continue from where we left off in the last class. In the last class we were studying binary decision diagrams, which is one form of representation of logic functions. So just to recapitulate quickly, that the picture shown here is a binary decision diagram for the function f equal to a and b. So corresponding to each variables we have nodes in the binary decision diagrams, and we have two types of edges. The bold edges are the ones which are taken when the variable value is 1, and the dashed edges are taken when the variable value is 0. So we see that when a is 1 and b is 1, the function value becomes 1, and when any of them are 0, then the function value becomes 0, which is what is the function f equal to a and b. Right. Now we also we were at the point where we were saying that suppose we have another function g, let us say there is some other function of a and b, let us say that is not of a, and then that would look like that when a is 1, then we go to 0, and when a is 0, then we go to 1. Okay. Now suppose I want to compute something like f or g, then how do I take these two BDDs and then create the BDD corresponding to f or g? Okay. So to do that, there are several BDD operations that are there, and we are going to look at them one by one. So the strategy is that represent data as set of OBDDs, express solution method as sequence of symbolic operations, and implement each operation by OBDD manipulation. So we can look at BDDs as sets, because effectively any Boolean function also represents a set. So it represents a set of valuations for which the function is true, and for the remaining valuations the function is false. So any set can be defined by a containment, can be defined by a Boolean function, and vice versa. So what are the algorithmic properties? That the arguments are OBDDs. So for the type of operations that we are now going to look at, the arguments are OBDDs with identical variable orderings. This is an important thing. They have to have identical variable ordering. So in our case, if you have f, g as two functions, then the variable ordering in a and in f and the variable ordering in g will have to be the same for us to apply these operations, and the result is an OBDD with the same ordering. Okay. We are going to come back to the closure property later. The apply operation, so there are broadly two types of operations that we are going to look at. One is called apply, the other is called restrict. So the apply operation takes two BDDs f and g and an operation called op. Op can be your regular Boolean operators like and, or, not, x, or whatever, and it returns a BDD corresponding to the function f of g. Okay. And it works by traversing the BDDs for f and g in a depth first manner. We are going to look at the algorithm shortly, and it uses the Shannon's expansion to compute this operation. So to understand how Shannon's expansion is used, suppose I have a function f, and let us say that the root variable here is x, okay, and then on this side I have the BDD corresponding to f, right, and on this side I have the BDD corresponding to f x restricted to 1, right, and then suppose I have another function g where also the top variable is x. Okay. So on this side I have g with x restricted to 0, and on this side I have g with x restricted to 1. Okay. Now when I do say f and g, say my op is and, then this is, I can rewrite this as x into f plus x bar into this is Shannon's expansion, and this with g x with g x bar right. So now I can rewrite this as that when I have x, then I have right, and then with that what do we have? Plus x bar zero right. Okay. So effectively what has happened? What does this look like? So what we are doing is therefore taking f with x restricted to 0, g with x restricted to 0, and computing BDD op of these two, right, and then we are computing BDD op of these two. So the effective BDD will be, it will have x as the root, okay, this will be f and g, the BDD corresponding to f and g, and on this side I will have the BDD of f and on this side I will have the BDD corresponding to right, and then recursively again from here the same operations will take place, right. Is that clear? So this is the way that the op will go. Now suppose what are we going to do if this is x and this one is some y? It is also possible. Suppose the function g does not have x, it has some y, right, or it has x but x is somewhere below, right. So now what we have to do is that, so let us draw that case. So you have, I have x here and I have y here. This was my f, this is my g. Now let us say that in the variable ordering x precedes y, okay. So in the variable ordering x comes before y, then there it is possible that there is some y node in these BDDs, right, in these BDDs. So what are we going to do therefore? So what we will do therefore is we will have to put y also in the final BDD, y will come ahead, okay. So for the BDD of f of g I will take the node y, right, and what am I going to do on this side and this side? So I will only expand out this one. So I will say that f of g is nothing but f of, and expand this one according to Shannon. So y times g with y restricted to 1 plus y bar times g with y restricted to 0, right, and then this is what, f of G y restricted to 1, right. So, in the BDD this times y, of course, okay, and this is the other term, right. So, on this side of the BDD I will have f of G with y restricted to 0. On this side I will have f of G with y restricted to 1, right. So, when I have x and y and x precedes y, so I did it the other way around. This is if y precedes x, then if y precedes x, then we are going to keep y, and then we are going to bring x down here on both sides, okay. So, basically take this function, let us say G1, let us take this function G2. So, we do f of G1 and we do f of G2 on this side. Is that clear? Let us see some examples, it is going to become further clear. Okay, so let us see what we have here. Consider a function, okay, this is restriction that we are talking about here. A restriction of f with respect to a variable x such that x is less than var f can be computed as follows. We are going to come back to restriction, so do not bother about this right now. Okay. Let us look at this one. Okay. Let us look at this example. So, I have this as one BDD, this as the other BDD. Okay. And let us say that in the variable ordering we have A precedes B, precedes C and precedes D. Okay. So, initially I want to do some operation between this function. So, this is my f and this is my g, and I want to do f of g. Okay. So, I am going to do A1 times B1, that is what I want to do. Okay. So, the root of the BDD is going to represent f of g, which is A1 of B1. Okay. See, this A1 B1s are the functions that these nodes represent, right. So, A1 is the function that this one represents, B1 is the function that this one represents, and as you can see, any node actually represents some function. So, for example, this node B2 represents the function D, right, and the node B5 represents the function C and D, right. So, now let us see, we want to do A1 of B1. So, that is what the root of the BDD is going to represent, and since both of them are the same variable, so therefore, we will expand both of these using Shannon's expansion, and therefore, we are going to have A2 B2 when A is 0. So, when A is 0, we have A2 B2, and when A is 1, we have A6 B5, right, this. So, intuitively what does this mean? That the BDD corresponding to A1 of B1 will have two child nodes. The left child node corresponding to A equal to 0, what is the variable here? A. The corresponding to A equal to 0, the function will be, the function that is represented by this node will be A2 of B2, and the function represented by this node will be A6 of B5. Then when you have A2 B2, now see, this is B and this is D, right. So, we know that we have to expand this one and keep this one as it is. So, if we expand this one, then what are we going to have? We are going to have A3 B2 when B is 0. So, the variable here is B. Okay. So, when B is 0, we have A3 times B2, this one, and when B is 1, we have A6 times B2, this one. Now what is A3 times B2 going to have? A3 times B2, both of these are D, so we will expand both of them, right. So what are we going to have? A4 times B3, and when D is 1 then we have A5, and when D is 1 we have B4, so A5 B4, right, alright. Okay. Now this part of the tree is done, so we backtrack and then take this side. Now we have to solve A6 B2. Now for A6 B2, this is C, this is D, so we will expand A6, right, and for C equal to 0, so the variable here is C, the variable here was D. So when C is 0, then we go to A3, so A3 B2, from A6 B2 we will go to A3 B2 when C is 0, when C is 1 then we will go to A5 B2, right. Now A3 B2 is something which we already encountered previously. So while the construction is done, the BDD manager will keep this information in a hash table that we have already done A3 B2, right. So then the function corresponding to A3 B2 is available in the BDD, so it is just going to make this edge point to that node, right. Now having completed this, it is going to backtrack right up here and then go down this one and then start with A6 B5. Now corresponding to A6 B5, both the variables are C, A6 and B5, so we will expand both of them. When C is 0, then we go to A3 and B4, right. So this is A3 B4. Now this variable is C. When C is 0, we go to A3 B4, and when C is 1, then this one goes to A5 and this one goes to B2, so it goes to A5 B2, right. So again you see we use the hash table to make it point to this one, right. So this is how the operation of the two BDDs are performed. Now note one thing, that what is the complexity of doing this thing? The complexity is that we traverse the BDD in a depth first manner. So whatever complexity we have for depth first traversal of the two graphs is the complexity of the operation, right. Then so this is the apply operation. Now let us look at okay. Now while we are doing this apply operation, it is very important to apply reduction every time. See, a BDD can blow up considerably if you do not apply the reduction. You remember we studied 3 different reduction rules in the last class. So while the BDD is being constructed, the reduction rules are applied to keep the BDD contained. So for example, for this without reduction we might have a BDD like this, but then you see that this one, for this one both the 0 and 1 edges are pointing at 1. So this node is going to be redundant, right. So if you remove this node, then and merge these two nodes, then you get the reduced BDD, which is this, okay. And all the time while operations are performed, in sync with that the reductions will be applied. Let us now look at the restrict operation. So apply is one fundamental operation where we take BDDs of 2 arguments and then we can apply any function on them, and or not, XOR whatever, using the same technique as we saw just now. And we have the restrict operation where given a function argument and a variable xi which is set to a constant k, which could be 0 or 1, we want to find the reduced BDD after that variable has been substituted with that value. So restriction is, as the name suggests, it is the substitution of one of the variables in the function with some value. So, the restriction algorithm will also work depth first. It will redirect any arc into vertex v having var v equal to x to point to hiv for x equal to 1 and lov for x equal to 0, right. What does this mean? That if you have a variable x which you want to set to 0, okay. So, suppose you have a variable x which you want to set to 0. So, if there is a node corresponding to x, right, and there is an edge going to some vertex y and the one vertex going to some z, then when you want to restrict x to 0, the parent edge will now be made to redirect to this, because x is 0, we know that. So, this edge is never going to be taken. So, drop this node out, okay, drop this edge out and make this point to this. Now, if there is no other incoming edge to z, then even z will go away, right, and so on. So, let us see an example. Suppose we want to restrict b equal to 1 in this, right. Now, if b is equal to 1, then you see this edge is never going to be taken, right. So, we redirect this one here, okay, and this node remains because there is at least another edge pointing to it, right. Now, look at this one now. This one has become superfluous because both of its edges are pointing to C. So, if you apply reduction, then this is the resulting BDD, right. Now, let us work this out in terms of a normal functional view of this. So, what is the BDD? What is this BDD? What does it represent? Can you tell me what it represents? Just see what it represents. So, you have A, B, C, right. Now, this is what? How do you read the BDD? What is F? F equal to, read out the min terms. So, AC plus A bar BC, okay, A bar B bar D. Is this a good way of doing things? You will have to traverse all paths, right. Instead, to read this, you start from here. What does this node represent? Function. This node represents D, right. What does this node represent? It represents C bar D plus C, right. What does this node represent then? This one by Shannon's B bar D plus B and this thing, right. So, that function here, that let me call this G. G is B bar D plus B times C bar D plus C, okay. And then what is F? F is a bar times this, right? Right. Now, if I substitute b equal to 0, b equal to 1 rather, that is what we did. If you substitute b equal to 1, what is going to be the case? This one will be 0. So, this term will drop off. Okay. So, we are going to have a bar, this one will c bar d plus c, right, and this is plus a c bar d plus c. This is a plus a bar. So, it is going to drop off and we are going to have c bar d plus c, right. Now, come to the final BDD that we got here in the computer. What do we have here? C bar d plus c, right. There are a lot of operations which are derived out of the apply and restrict operations, okay. And it results in an OBDD with the right variable ordering. All of these have polynomial complexity, polynomial in the size of the BDD, right. Remember that the size of the BDD can be exponential in the size of the function, right. If you write the minimized expression of that function, then the BDD can be exponential in the size of that. But given a BDD, the operations are polynomial in the size of the BDD. One interesting thing that we often require is quantification. So, suppose I want to find out that given a function over, suppose f is a function over variables x1, xk, okay, right. Now, if I ask you that, if I ask you there exists x1, there exists x2 dot dot dot, there exists xk, f of x1, x2 dot 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 xk, what is this? What does this represent? This just checks whether f is satisfiable, whether there is any valuation of x1 through xk for which this is true, right. So, this whole thing is true if and only if f is satisfiable, right. Okay. And when do we say this one is true? When do we say this one is 1? Then when this is valid. We say that this one is true when this is valid, and this is actually checking for satisfiability. Right. Now, you can say that, okay, I want to find out that for all x1, does there exist x2, xk such that is this the same as the previous one? No. No, because it could be the case that for this function you can only satisfy it by setting x1 equal to 1. It may be the case that every satisfying valuation of x1 through xk must have x1 equal to 1, in which case the second one will fail, right. So, this is quantification. Now, the complexity of the satisfiability grows with the number of alternations that you have with these, right. So, for example, if I ask, if here we have only one alternation, okay. So, if you have everything as x1 through xk, everything is existentially quantified, you have satisfiability. If you have everything is existentially quantified, this is true for only valid expressions. For all valuations it is true, right. And then you start alternations, and with each, so this is in which class? This is in NP. Where is this? Co-NP, right. And then you now start growing in the polynomial hierarchy. So, in the, when you have one level of alternation, you are one level up in the polynomial hierarchy, and when you have complete alternation, so for all x1 there exists x2, for all x3 there exists x4, and so on, right. And then for x1, this is called, you know, number of alternations is arbitrary, then this is called a quantified Boolean formula. Quantified Boolean formula, okay, or QBF. Now, this checking this satisfiability is NP complete. This checking the truth of a quantified Boolean formula is a p-space complete problem. So, it is at that you can characterize any of the classes in the polynomial hierarchy with the appropriate number of alternations in a quantified Boolean formula, right. Now, why is this quantification useful? Because we want to find out whether the function can be made true under different variable valuations. So, can I treat a variable as a don't care? If it is don't care, then the function value does not depend on it regardless of whether it is 1 or 0, right. So, if there is a don't care variable in your function, then it does not matter whether you assign it 1 or 0, right. So, you can eliminate that, and eliminating variables can reduce the size of your verification problem, right. So, that is why quantification is a very important requirement. Okay. There are several digital applications of binary decision diagrams. People have used it for combinational equivalence checking. Combinational equivalence checking is simple. You have function f and you have function g, combinational functions. You know that if they are having the same set of variables and they are in the same order, then the two BDDs are going to be identical, right. So, I can check whether they are equivalent like this. So, to find out whether an adder is an adder, whether multiplier is actually a multiplier, combinational multiplier, these things we can check easily by using binary decision diagrams. Then we can also check for FSM equivalence. We are going to come to this in this combinational logic and build the BDD for the combinational logic of the other FSM, then by comparing the two combinational logics I can conclude whether these two FSMs are equivalent, right. Now what happens is, often what people do is that they build a finite state machine and then they optimize the combinational logic. This optimization can include retiming, moving some logic from behind the flop to front of the flop, okay, and then adding some additional logic here to bring down the delays and all that, right. So people do a lot of optimization here, and all the while they want to make sure that the functionality does not change, right. So how do they do that? They do all those perturbations in the combinational logic and then again do a equivalence checking between the two combinational logics, and for that you can use the BDD, right. Now if these two state machines do not have the same state encoding, then you cannot do this equivalence checking like this, okay, and we are going to see later on there are other methods for doing that equivalence checking, right. But there is a lot of application of this kind of equivalence checking, because there are many cases where you retain the same state encoding, but you tweak the combinational logic to make it more delay efficient, power efficient, retime the circuit, and then want to check whether it still remains equivalent. We will see some of those tricks later on. Then we have symbolic simulation, where you want to simulate the circuit not for one inputs but several inputs at the same time. So BDDs are used for doing symbolic simulation. We are going to see later on how we can do property verification using a trick called symbolic model checking, which will be discussed in a later chapter. BDDs have been used in synthesis. They have been used for don't care set representation. They have been used for state minimization. They have been also used for sum of products minimization. In testing also they have been used for test generation and false path identification. These are some of the popular BDD packages. Now, BDD packages are widely available. What they have is it comes with a set of functions. So you can start defining your functions by calling these functions. So you first define the set of variables, then use two variables and say that f is AND of these two, then use f with another g to define f or g, right, and that way you can grow the function for your the BDD for your function, right, and then you can do all the apply, restrict, all these. For each of these you have library functions available in the BDD package. The most popular BDD package that is used today is the CUDD, or the Colorado University Decision Diagram package. Then there are several others like the CMU BDD and the Stanford and the Berkeley BDD packages, which were one of the earliest that came along. And there is a website www.bddportal.org, which maintains the different BDD packages which are available and gives some details on each of them. These, by the way, are in the public domain, so one can always download them and use them. Well, now what we are going to look at is how we can use BDDs to do finite state system analysis. So the system is represented as finite state machines. Now see, FSMs, okay, let me just skip through the usage part and let us see how we can do it. Okay, what is an FSM? How do we represent a finite state machine? We know that BDDs can represent sets, okay. When we are representing combinational functions, the set that the BDD is capturing is the set of valuations of the variables for which the function is true, right. Those are the paths which lead to the one node of the BDD, right, and it also keeps the remaining vectors for which the path leads to 0, right. Now, when we talk about a state machine, finite state machine, what is that set? How can we think of a finite state machine as a set? So, the basic thing of a finite state machine is the transition relation, right, the state transition relation. So, we have the set of state bits and we have this transition relation. So, suppose I have a finite state machine which looks like this, that it goes from 0 0 to 0 1, right, to 1 0 and then back here, right, and the state 1 1 is a separate state. Suppose this is a finite state machine, right. Now, if I write down this transition relation for this, I will have present state and I will have next state, right. Now, in the present state next state, let us see what happens. From 0 0 I go to 0 1, right. From 0 1 I go to 1 0, from 1 0 I go to 0 0, right, and this one remains here. So, from 1 1 it is always 1 1, right. Now, see, these are the valid transitions, okay. These are the valid transitions. Now, there are many other 4-bit vectors apart from this. Which ones? So, we do not have, for example, how many 4-bit vectors are possible? 16. We have only 4 here. So, there are 12 others. What are those 12 others? Let me write them down below the line. So, from 0 0 to 0 0, from 0 0 to 1 0, from 0 0 to 1 1, okay, and so on. There are the remaining 12 ones. Now, suppose we define a function f and say that for these the function value is 1, for the rest the function value is 0, right. What does this function represent? This function represents a logic which takes two inputs, the present state and the next state, and this logic, which is called f, becomes 1 if this present state next state combination is a valid transition, otherwise it produces 0, right. Now, you see the equivalent representation of this finite state machine as a combinational logic is this transition function. This transition function is no different from this one, this combinational logic. So, if it is the BDD for this combinational logic that we can build, right. This is the transition function. This is the function that we have written down here, okay. Now, if I create a BDD for this function, then this function, in this function for 0 0 0 1 the path will lead to the 1 node of the BDD, but for 0 0 0 0 the path will lead to a 0 node in the BDD. And what are going to be the state variables of this BDD? They are going to be 4 variables, S0 S1 for the present state and N0 N1 for the next state. So, there will be 4 variables in the BDD, right. Let us see an example. So, here is a finite state machine where you have these 0 0 0 1 1 0 1 1 at the different states. So, there are 4 states here. Now, this is the BDD corresponding to this particular state machine. Now, let us see that, let us see some of the transitions. From 0 0 to 0 0 is a valid transition here. So, let us see what happens when so the encoding here is O1 O2 are the old states, present state, N1 N2 are the new states, okay. So, 0 0 0 0 goes where? So N1 is 0, O2 is 0, so it goes to 1. So 0 0 0 0 is a valid transition, right. Let us look at the case where I go from 1 1 to 1 1, right. 1 1 to 1 1 is a valid transition. So see 1 1 1 1 valid. Let us look at an invalid transition, say from 0 1 to 1 1. So if we have to go from 0 1 to 1 1, so then N1 N2 are 1 1 and O1 is 0, O2 is 1. So N1 is 1, N2 is 1, okay, and O1 is 0, and we end up in 0. So you see there is no transition from here, okay. So this represents the BDD of the state transition relation. Now the question is, what do we do with this BDD? So what we can do is we can do reachability analysis in the state machine. So given the transition relation of the BDD, okay, the BDD for the transition relation, and given a target state and given the initial state, my problem is to find out whether I can reach the target state from the initial state, okay. So what do? We start by the following thing, that we start from the initial state, okay. What we are going to do is we are going to go breadth first. So in the first iteration we will start with this one, right. Then using the transition relation we will find out the set of next states of this state. So we are going to keep the set of visited states in a BDD called R. So R0 is the initial BDD which contains only 0 0. Then from R0 we will construct R1, from R1 we will construct R2, from R2 we will construct R3. Ri denotes the set of states reached, visited within the first I iterations, right. So we keep on adding states into the BDD with each iteration because we are visiting more and more states. Now this is a finite state machine, so somewhere we will stop and we will see in 2 successive iterations the BDD has not changed, the set of states has remained the same. Then we have found out the set of reachable states from the initial state, right. If we still do not have the target state, then we conclude that the target state is unreachable, right. So let me reiterate once again. I am starting with the initial state. From the initial state I am growing the set of reachable states. So I am in the initial state. Then in the first iteration I find out the states which are reachable from the initial state, right. In the second iteration I grow this set to find out more states which are reachable from here, right. So in this way the set of states keep growing. Now because this is a finite state machine, at some point of time we will have visited all the reachable states from the initial state. If we have not yet visited the target state, then we know that the target state is not reachable, right. So R0 is 0 0, R1 is, when we apply one loop with the transition relation, it is going to produce 0 1, it is also going to produce 0 0 again because of this edge, right. it is one single BDD operation which is going to cover both of these transitions. That is the beauty of the thing. Then from from this R1 we apply another BDD operation to get R2, which is now going to have 1 0. Then in the next iteration we generate only 0 1 and 0 0, but both of these were already visited. So we will see that in R3 and R2 the set of states that have been reached are the same, right. So we stop here. Now if 1 1 was the state that we were trying to reach, then we have not reached 1 1, and we say that 1 1 is unreachable from 0 0. Okay. Now this termination, where for two successive iterations the BDD does not change, is called a fixed point. Okay, it is called a fixed point. Okay. Please remember this term, because we are going to use this term quite frequently in the near future. Now let us see how this is done using the BDD. Okay, how does this traversal take place using the BDD? So we start from 0 0, and this is the transition relation BDD, right. Now when we want to find out what are the next states of this state, what do we do? See, what does this represent? This represents the next state, this is the present state, right. So the present state is 0 0, we want to find out what are the next states. So what do? We substitute this present state into the BDD, right. Okay. So suppose we substitute this by 0 0, so O1 is 0, O2 is 0. Okay. What is the BDD that we get? We get this BDD. Now see, what does this BDD have? Which vectors are is it accepting now? N1 is 0 and N2 is don't care, right. So 0 0 and 0 1. So the next states of 0 0 are 0 0 and 0 1, right. So let us go up here. See, the next states of 0 0 are 0 0 and 0 1, right. Now how do we find out the next set of states? So what we do is we rename this to O1 and rename this to O2, and again AND it with this BDD. If we AND it with this BDD, again this is going to get substituted here, and the resulting BDD is going to show you the next set of states, right. And you are doing an AND with the whole BDD, because see, what you are doing is you are taking R0 old, this is the BDD for R0 old, and taking the AND with the transition relation, because this is going to substitute these into this and give you the set of next states, right. In the next step, what are you going to do? See, this is going to be your R1. So in the next state you are going to take R1 and delta of old new, right. This is how repeatedly the next states will be computed, right. So this is the, after you get this, then you rename this to O1 and then again do the same thing, right. Okay, clear? So just to summarize, what's good about OBDDs? They are powerful operations for creating, manipulating and testing. Each step has polynomial complexity. Okay. You can maintain the closure property, that is each operation produces a form which is suitable for other further operations. and they generally stay small enough. Take this with a pinch of salt. I mean, small enough for circuits of moderate size, but for large circuits they almost always blow up. What's not so good about OBDDs? It doesn't solve all problems. Multipliers is a class of circuit for which they always blow up, and it's important to choose a variable ordering, and some types of operations are very hard to implement using BDDs. Right. So, there are several variants of BDDs which due to lack of time I will not be able to cover, but these are things which have been introduced later on to get around the problem for OBDDs for certain classes of functions. So, that includes things like zero suppressed BDDs, then multi-terminal BDDs, then edge valued BDDs, and binary moment diagrams. So, maybe sometime offline we can discuss these different types of BDDs. Okay. So, thank you very much.